right, it's about that time. Good afternoon, everybody. This is Arun Thiraviam, and I am a simulation product specialist with GoEngineer. Thank you for joining me on this webinar this afternoon, where I will be presenting some of the capabilities of SolidWorks Simulation, the finite element analysis tool that's integrated in the CAD software. Before we begin, I'd like to inform you that your mics have been muted during the presentation, but you'll have the opportunity to shoot me questions through the chat feature at the end of the webinar. So, if you'd like to live tweet your comments, please use the Twitter handle @GoEngineer so we know about it. Thanks. All right, let's get started with the 4 flavors of SolidWorks simulation. Now, when it comes to product design, there are many engineering challenges involved, in making something work. For instance, consider this device we have here on the screen. This is a device developed by a company called Myomo for patients with limb paralysis. This myoelectric prosthetic, as they like to call it, restores movement to the user's arms via electromechanical circuitry, to overcome the paralysis. Now, if you caught any of our 2017 rollouts, this was a hot topic of discussion, the holistic usage of some of the SolidWorks tools in order to come up with this design and essentially develop it. Now, taking a look at this device, of course, some of the obvious challenges from an engineering perspective are, these 3 challenges. Strength. Well, the device needs to be able to tolerate all the operational loads that it experiences. It could be holding the circuitry in place, all the constant button pushing, or even something as simple as, opening the battery case for replacement. Thermal performance. There's probably some circuit board in here that gives the device its intelligence, and any power generating component generates heat. So, we need to ensure that this product does not overheat and, does not harm the customer. Finally, manufacturing. Now, since this is a plastic enclosure that houses all the circuitry, there are challenges involved in injection molding, in order to injection mold these components with the least number of aesthetic and structural defects to ensure fit and function. Now, taking this device apart should give you an insight into how compact this design is as well. Now, most engineering challenges involve balance, which is not a very straightforward problem to solve. For instance, when you take strength, now there is a weight element involved. Any additional feature, such as a little rib that you add to strengthen the component or increasing the wall thickness, will not only affect manufacturability, but it will also affect how the component is packaged and the overall weight of the component. Those are, again, opposing goals. Now, thermal performance. Now, can we heat sink the part without compromising its compactness? Now, as far as thermal performance goes, you need enough airflow within the component to carry the heat away from whatever heat sinking methodology that you figured out. Now, this is only scratching the surface with all the problems that this component might undergo, during its performance. So we need to be able to predict all these problems beforehand, and that's when, simulation comes in handy. Now having access to CAD and simulation tools simultaneously within the same environment, we can definitely streamline this process for finding this balance and, coming up with mature designs. But there's an overarching benefit behind these tools driving innovation. It's not only form, fit, and function, but it's also time to market. Now, we live in a competitive engineering space, and innovation needs to be backed by the ability to essentially create and deliver products, which is what these virtual analysis tools that I'm about to demonstrate to you aim to do. Now, there was a recent survey conducted by the Aberdeen Group about 2 years ago on the top challenges in the NPD equation, the new product development equation, and shortened product development schedules came up as one of the key elements, one of the bigger challenges, even above compliance with regulations, developing low cost products, and so on and so forth. So through design simulation, we aim to shorten the design development process and the number of prototyping iterations you need to go through before coming up with a mature design. And I'm about to show you some of this capability with SolidWorks Simulation. Now, like I said, SolidWorks Simulation is a finite element analysis tool. With this, we aim to accelerate the product development process, so to speak. We are able to test for strength, durability, and thermal performance within the same interface for a variety of designs and materials. Now, when we consider the capabilities, though, we have about 4 features, or 4 flavors, as I like to call it. And even when finite element analysis is concerned, generally, you can divide the principle of structural analysis into four flavors. Now, let's talk about the first flavor, which is a static analysis. Now, static analysis is relatively straightforward to understand. You're essentially trying to balance the strength versus lightweight equation. Now, how light can you make a product without compromising its structural strength? Now you see this graph here, it represents the stress strain curve of, a little piece of material that's depicted here. Now stress strain curve essentially indicates how elastic a material is, and relying on the linear range of this elasticity, we predict the strength of whatever component that this material, that we utilize this material to make. So the static analysis, given the material properties and the loading conditions, gives us insights into the strength of a product. Now for our test case today that I'm going to run through these 4 flavors, I've actually taken something really simple but really useful. For instance, this iPad mount. You either mount in your car, mount it on your living room table, but this mount needs to be strong enough to be able to take the load of the iPad and also any kind of vibration and thermal loads that it may experience. Now, what we were able to do with this is focus on this little arm design, and we were able to test this arm design for the various loads that this experiences to come up with the best arm for this little, iPad handle. Now, I'm going to quickly jump into the software to walk you through how I got into these results and how I utilize SOLIDWORKS Simulation to kind of, make these decisions. Now, jumping into SOLIDWORKS, you've seen this interface before. I'm going to open up the iPad mount. Firing up the iPad mount gives me access to the features and the parts that make it. Now, if you've used SOLIDWORKS long enough, you understand how the interface works. You have the command manager that gives you all the buttons that helps you set up a product or create a product. And you have the feature manager that populates all the features that you've used to build the model. Now, as a philosophy, since SOLIDWORKS is gravitating gradually away from being just a CAD tool to a complete solutions product, if you jump into this little add-ins tab and you grab the simulation button, what happens is you add the structural simulation solver into the CAD interface. Now, once you have the structural simulation solver added, the command manager updates to essentially have the simulation tab. Now, the simulation tab helps you or gives you access to the buffet of analysis tools that you can use to test this product. And you can see some of these analyses that I've set up beforehand populate as tabs at the bottom of the window. So, after you run the analysis essentially piggybacks on the model. So whoever has an access or has a license of SOLIDWORKS Simulation has access to all of these studies that you've tested. Okay, great. Now, how do we go about setting up a simple structural study? Now, I'm going to grab the little new study button, and that's going to give me access to this analysis buffet. Now, I'm going to start out with a simple structural test. I'm going to name the analysis structural one. I'm going to select the static button, but there are other analysis tools that you can use as well. You have access to all the 4 flavors here. Now, once I hit the green check mark, the tree is relatively straightforward. You follow a serial process going from the top to bottom, setting up the analysis and its material properties and the loading conditions. Now, as far as the properties go, most of these properties are derived directly from the CAD side. But if you want to add a custom material property, you're able to access the material database right from this parts tree. Now, the material database has everything from metal alloys to plastics. Since I'm using a polypropylene or some sort of a copolymer, I'm going to pick that off of the material database. Now, selecting a material gives you access to its material properties. Now, anything that essentially you need in order to justify the structural strength is highlighted in red. So if you don't see a property, you can create custom copies of this material property and add in those properties. So once I have selected the PP copolymer, I'm going to hit apply and I'm going to hit close. And you can see that this is very GUI driven. Now, anytime you make an assignment, you see a little green check mark next to the assignment. Now, since I'm running an assembly level analysis, I need to specify not only the constraints of individual components, but also how each component interacts with each other. You can see that for this assembly, I've removed pins because typically when you run these kind of fastener analyses, you only want to figure out what shear forces and axial forces these fasteners experience. So you pull out the CAD model and you use the pin connections that are built into simulation. So if I right click the connections item, I have the pins tab. In order to create a pin, they're relatively straightforward. I grab a set of concentric faces and then I specify the elasticity of the pin. Here I'm specifying that this pin is completely rigid from rotation and translation. Now once I have these 2 components pinned, now I need to assign the pin between the mount and the handle. Going back to my connectors tab, I'm going to grab the pin item again, and I'm going to simply just grab a set of concentric faces and specify that these concentric faces are rigid. Now, once I have both the connections set up, I need to specify how these components interact with each other. By default, SolidWorks assumes that each of these components are bonded together, meaning this handle is not allowed to pivot about this fixture, and this little mount is also not allowed to pivot about the handle. Now, in order to get a quick sanity check, you can jump into visualization plots that help you visualize what kind of connections have been established between components. While a bonded connection, meaning a tight contact, has been established between the iPad case and the handle, which is okay, a bonded connection between the handle and these two components seem a little detrimental. So in order to quickly modify those connections, you can create contact sets, and you can have the software automatically find contact sets between mated entities by hitting the find contact sets item. Now, as soon as I hit the find contact sets item, I have the 4 sets of contact pairs defined between each of these components. I specify a sliding or a low penetration contact set, and then I add the contact sets to the tree. It's really simple, a 2-step contact creation process. And anytime I create a contact set, if I jump into the connections item, I can visualize what kind of contacts exist right now after I create the modification. And you can see, as expected, these are allowed to slide freely and are only controlled by the rigidity of the pin as far as the motion of the arm goes. Now, once you have the connections defined, you can go down the tree and specify how this component is constrained to the environment. Now, through this little fixture interface, I'm able to select the face for the fixture, and I'm able to select the type of fixture that I need. Now, since I'm constraining this on all degrees of freedom, I'm just going to select the back face, and I'm going to use fixed geometry. But I have access to some advanced fixtures where I'm able to control individual degrees of freedoms as well. But I'm just going to stick to the fixed geometry for this one. Now, besides this, what is the external load? You essentially want to see how much the iPad sags if mounted onto this fixture. So the only load that's operational is the weight of the iPad, and how you can turn on the weight is essentially by applying gravity as an external load. So if I right-click external loads, I can grab gravity, specify the direction of gravity by selecting the plane as a reference. Make sure I reverse the direction so it's pointing downwards. And that's it, I'm ready to run the analysis. Now I'm going to jump into something that I've already set up just to show you the tree and to spare you actually waiting for me to run this solution. It takes about 10 seconds to run. Now you can see the meshing process is also pretty straightforward. We primarily use a solid tetrahedron mesh, and if I can show you the mesh, the mesh has the intelligence to actually resolve areas of curvatures with high density elements, and to ensure that these small critical features are resolved enough to give you reasonably accurate results. Now, like I said, after I do all this and I hit run, the first thing I get is essentially the structural stress distribution, or the von Mises stress. Now, while ABS or most polymers have a tensile strength of around 40 to 50 megapascals, this indicates that the max stress on this component is just 5 megapascals. And you can see a majority of that stress is concentrated in this area. You can quickly use visualization tools such as the isoclipping tool to visualize the load path or where the stresses originate. So in that way, if you're making a minor modification, you know immediately that you need to keep away from these areas. So right now I'm indicating all the areas that are over 1.4 megapascals that constitute a factor of safety of almost 20. So you can see that this design is extremely strong, and the weight of the iPad is not going to essentially warp this or cause permanent deformation. Now, besides that, like I said, you can see fastener loads as well. If I actually hit the list connector force button, I'm able to plot the force on each individual fastener to ensure that I have the right size of fastener for this application. Excuse me. Now, once that's done, I also want to see how much this thing is displaced. Now, the success criteria here not only relies on the strength, I also want to see the amount of sag. And the sag here indicates about 2 millimeter, which is about 2 to 3 millimeter, which is absolutely insignificant. Now, this only gives me a lot of room to actually modify this design and understand if removing material is going to improve or is going to hamper the design performance, like the sag or the structural strength. Now, in order to do that, I don't have to keep running the analysis on the entire assembly. I can actually do a part level analysis by opening up the part and setting up some really simple constraints. So I'm only going to open the handle because it's the primary load-bearing entity. As soon as I open up the handle, here's my handle model. I have the simulation solver already added in. I'm going to head new study. I'm going to set up a new structural study. I'm going to set the material property of the arm similar to the material property I used before. I'm going to jump into plastic, PP copolymer right here. I have the elastic properties built in. Going to hit apply. Now, as far as the fixturing goes, since there are no connections, I don't have to worry about that. I can simply apply a fixed fixture, if you will, at this cylindrical hole, simulating the rigid connection with the pin. And as far as the external loads go, I know an iPad weighs about 1.5 to 2 pounds. So a majority of that load is going to be transferred to that face. Now I'm going to set this to pounds, and I'm going to specify once I have the direction specified, I'm just going to set this to let's say about 2 pounds. Now once I have the fixture and the material properties defined, I'm going to head into the mesher, specify the mesh density that I need, and I'm going to hit the green check mark. That's then going to divide this into small elements. Once the element division is complete, all I need to do is run the analysis. And as expected, you can see the performance is really similar to the assembly level analysis. You have about a 2 mm sag in the arm. Now what I can do with this is I can actually apply the same study across multiple configurations. You can see here I have 4 different configurations that control not only the thickness of these ribs, but also the width of the arm itself. Now let's say I wanted to run a quick analysis on a thinner arm. All I need to do is use these quick productivity tools and hit copy study, call the static 2, and ensure that I'm duplicating all the elements into the narrow configuration. Now once I have that, I have and I update the tree. The model updates. It has all the boundary conditions that I set up in the previous analysis and the material property. All I need to do is update the mesh and run the analysis. Now usually when I update the mesh and I run the analysis, in case the component is deforming more than it does, if it's exceeding the small displacement assumption, if you will, there's a little decision solver message that pops up that says, hey, this is deforming a lot more than its elastic region permits it to. Would you like to run a nonlinear analysis? Now for this, I'm going to assume that deformation is not going to have a significant effect, just to see how much more my displacements have increased. So when I look at the displacements, you can see that using the narrow configuration, my system has about doubled, or the sag is about doubled. So duplicating these studies about different configurations, I was able to come up with the design that essentially reflected the least amount of deflection and demonstrated the most amount of factor of safety. Now just going back to my presentation, like I said, I tested this across 3 different designs and I was able to come up with something that worked. Now sticking to the arm, I'm going to explore the second flavor, which is the dynamic. While static analysis relies on your component having static equilibrium and static loads, where the only response of the component is through deformation, structural deformation. Now dynamic analysis allows you to put in vibration loads or time varying loads. Now there are different kinds of vibration loads that we can put in. We can put in time varying sawtooths such as these, or we can put in full on harmonic loads such as this little sinusoidal input. Or we have a random vibration and response spectrum analysis tool that is able to process these kind of random vibration inputs to actually calculate the peak frequency the peak frequency and the peak response of the component during this random vibration sweep. Typically, you get these curves that represent these random vibration curves from MMPDSs or mill standard, and we are actually able to take inputs from the mill standard and MMPDS in order to run these kind of dynamic analysis to look at the structural response for a time varying loading or an impact loading. Now here's a little sample of the output I had. I measured essentially the strength of the tip of this little arm for a sawtooth input. So I actually added an impulse of about 1 G. So essentially this was accelerated by 1 G and decelerated immediately. And I wanted to see what the residual response was or what the peak response was. Now I'm going to show you how you can set up such a dynamic analysis and what kind of results you can get from the dynamic analysis tool just within SOLIDWORks. Now I was actually able to run the dynamic analysis through, through the assembly. Now an important aspect of running a dynamic analysis is to run a frequency analysis. Now a frequency analysis essentially gives you what the modal response is or what the resonant frequencies of the system is. So if I were to put this on a vibrating object, now if the object vibrated at any of these given frequencies, now these are the frequencies that are essentially going to excite my component to the point that it exhibits the most amount of response or the most displacements. So I need to make sure I create this design so that these set of frequencies are outside the loading frequencies that this could experience. Now once I have the frequency analysis, setting up the dynamic analysis is straightforward again. I hit the new study, I select the linear dynamic button, and that gives me access to some sub-analyses that I can run. Now since I'm going to apply a spike, which is a time varying load, I need to put in the modal time history analysis. Now with the modal time history analysis, the component setup is the same, the tree is the same. The only difference being, jumping to an analysis that I've already set up, is in the loading condition, instead of applying a force or a g-force, I specify base excitation. So a base excitation is a load by which I can apply the g-force to the fixture. So the excitation essentially originates at this fixture, and you essentially get to see how this excitation transfers from the fixture to the component and causes this entire component to vibrate. For instance, if I can show you just the response of this little random vibration loading, you can see the direction of gravity is this way, so I'm applying a spike that is in the negative z direction. Now getting a quick animation actually gives me real time how this is going to whip on the application of a spike. Now you can see that during this whip as well, I've exaggerated the deformation to 70 times, so the 1g spike is essentially not going to harm the component. So not only have we justified the static strength of the component, we've also justified the vibration strength of the component. Of course, I can run this analysis for longer to see this entire component wobble, but then I knew that the vibrations would damp out eventually, so I only looked at a couple of microseconds of the analysis. Now, a couple of key factors in order to set up the analysis, I'd say two factors. If I actually edit definition on the base excitation load, you specify what kind of excitation you're applying to the fixture and what kind of curve you're applying for the excitation. Now, besides that, in my study properties, I will essentially need to set up how long I'm running the analysis for and how often I am running the calculation. So I need to make sure I run these calculations as often as this has the ability to vibrate. Yeah, that's about it. Now, just jumping back to the presentation, as I said, with the dynamic analysis, we are able to test for vibration performance, where we are able to take a whole host of vibration inputs, which can be in terms of harmonic sinusoidal inputs or spikes, such as this sawtooth right here, or even random vibration or response spectrum inputs that has really random excitation, time-based excitation curves like this. Now, jumping into our next flavor is a nonlinear analysis. Excuse me. The difference between the static and the nonlinear is that, well, there are three differences. With the nonlinear analysis, if you remember, with the weaker arm, we had a little warning that said excessive displacements. Now, this excessive displacement essentially causes the stiffness of the component to change, and we need a way by which this change in stiffness and the change in the shape of the component is updated within the software when it calculates what the external force is actually doing to it. We call this geometric nonlinearity. Besides that, if you'd like to simulate components that have weird materials like plastic, or you'd like to study post-yield behavior of metals, like beyond the yield point, you want to see how metals or plastics permanently deform, or if you want to see hyperelastic materials in action, such as rubber, you're actually able to simulate all of that with material models that are built into the software that help you put in the stress strain curve. The final analysis is contact. Now, contact is really essential because when you take contact between two entities, depending on their elasticity, their point of contact or the area of contact change drastically. That affects the stiffness of the contact interface. So if you want to study a contact analysis accurately, you'll need to run nonlinear analyses. Now, how did I use nonlinear to test this design? You can see through this little animation, the iPad needs to clip onto the mount. So I wanted to see what is the stress distribution on the mount during this clipping process. Pretty straightforward analysis to run. I also wanted to see what is the force required in order to execute this clip. The clip essentially opposes the iPad through the friction between the contact, and how much force do you need to overcome this friction force so that it snaps in. So this is a graph showing you during the assembly process, the increase in force that's required, and it comes up to about 0.03 pounds, which isn't much. I'd say it's about 0.1 pounds because I ran the analysis on a quarter model, so I'd multiply this about 4 times. Now let me show you how nonlinear analysis works just within the software. Now for the nonlinear analysis, I didn't want the entire model, so instead I only took a slice of the model. So all I wanted was the iPad and the clamp itself. And since the clamp is symmetric, I sliced the model to 1/4 of its original shape. Now while setting up this analysis, I'm able to head in and grab new study, grab the nonlinear analysis tool, and hit the green check mark. Now with the nonlinear analysis tool, the only change I've made for the setup is to indicate to the software that these are going to be symmetric. This is a part of a larger component, and how I can do that is just through fixtures. If I jump into fixtures and I select the symmetry option, I'm able to grab each of the faces of symmetry, and the software virtually generates the entire component for you for the analysis. Just make sure that you do this to all the components that you have determine the symmetry for, Now once you have that set up, the rest of the analysis setup process is similar. Now the only other thing you need to add is that you can see that I've assembled this iPad to have a little distance between the final assembly. Now I'll need to apply this distance as an input. I'll need to move this to about 3 or 4 millimeters so it actually goes over this hump and it assembles in place. Now in order to do that process, I'm able to I'm able to access the prescribed displacement item from the external loads, specify the surface of the displacement, specify a reference that controls the direction of displacement. In this case, I'm going to use the front plane. Now the benefit of using the front plane is that I'm able to control the direction of displacement through these little icons. Now since the Y direction is the direction of displacement, I can activate the Y, make sure these arrows point to the direction I want them to move in, and specify the 3 millimeters that I need in order to assemble this in place. As usual, I have this analysis already run. I'm going to show you some of the results. The only other additional fixture that I added here is that I hinged this, I fixed this completely so that it represents the pin contact. Now I'd like to show you just the animation of the result, and you can see that this result animation is actually done and represents the entire model. So you can choose to either analyze just the quarter model, or you can display the results for the entire model. So you can see it's in the final assembled position right now, but to get to that final assembled position, I was able to move the component and essentially clip it in place. Slow down this animation here so that it's a little clear. And you can see or study the performance of this little clamp due to this assembly process, and you can see a majority of the load is actually being taken by the tip of the rib right here. But again, that load isn't too great. It's about 2 or 3 megapascals. I reduced this for so that you're able to see the stress hotspot clearly. Again, a couple of key features is just your ability to assign a displacement load, and you're able to vary this displacement in time as well. And this is a key benefit of running a nonlinear analysis. So anytime you have a plastic clip or a snap fit kind of assembly analysis, you typically go to the nonlinear analysis because you have contacts, you have large change in shape, and you need the solver to keep track of that change in shape while it's actually being loaded. And that's about it. Now, just jumping back to the nonlinear, actually I went a little ahead of myself here. I wanted to show you how I got the result force. So if I right-click results and I grab the result force item, I'm actually able to select the face that I'm applying the load to, and I'm able to get a response from that face. Now, while this shows me that I have about 0.016 newtons applied to that face, I can grab the response graph to essentially study how the force varied during the entire assembly process. Very popular technique, again, used for the assembly. Now, just jumping back to the presentation for the final flavor. Now the final flavor of the analysis is just the thermal analysis. Now as far as thermal analysis goes, there are three forms of thermal analysis. There's conduction, convection, and radiation. Conduction is heat transfer between components in contact. Convection is heat transfer between fluids and solids. And radiation is essentially, it's magic. It's a component heats up to a temperature where it starts emanating electromagnetic rays. Now we are actually able to simulate all three forms of heat transfer, except in convection. Although a fluid dynamics tool is better because it's able to simulate both the solid and the fluid media, we are actually able to fool the software or simulate the presence of a liquid by applying convection coefficients. Now what I wanted to do here is essentially test for thermal warpage. So what I did was I ran a thermal analysis initially to study the non-uniform temperature distribution. You can see that this gets to about 100 degrees for the temperature distribution that I've applied, for the thermal conditions that I've applied. And based on this 100 degrees test distribution, this is how the component warps. So it undergoes a 0.5 millimeter warp in the y direction on all four limbs. Now, is this warp going to affect the clamping force applied to the iPad? Is the iPad going to slip out and fall? So that's the kind of information you can get from just running a really simple thermal analysis to see the influence of temperature on the structure. Now, just jumping back into SolidWorks to show you what that setup looks like. Again, ran it on the entire assembly. Now, for a simple thermal analysis, a big condition is that you need to set up two thermal inputs. You need to set up what is the source of heat and how is the heat being dissipated. Now, as far as the heat dissipation goes, you'll notice as soon as I select the convection button, it indicates how what are the surfaces that are in contact with the liquid or the air, what is the temperature of the air, and how quickly is this losing heat to the air around. And finally, I specify the heat power. Since the iPad is going to be in contact with this surface, I just assumed a 1.5 watts being transferred into this surface. And since plastics have a tendency to really hold heat, this is the temperature distribution. Again, using ISO clipping tools, I can actually cordon off areas that are over a specific temperature threshold. So if I want to see all the areas over 75 degrees, well, that's the majority of the component. So let's see all the areas over 80 degrees. Oh, that's also the entire component. Let's say 90 degrees. Oh yeah, 90 degrees. There it is. So you can see a majority of the clamp is over 90 degrees. And running a structural analysis is straightforward. Now from the thermal analysis, I'm able to transfer in the structural analysis load by just suppressing the gravity load and applying thermal effects from the study that I've already created. So if once I grab the thermal effects, I can have multiple thermal effects. I can say okay, and then all I need to do is mesh and run the analysis. Voila, there you have it. So you can see this deformation is kind of symmetric and something that you definitely need to watch out for. We also have the ability to extract this deformed shape to see how the final iPad, if the iPad fits the final form of this model. Now, just wrapping things up. Now, what I did was I walked you through the 4 flavors of analysis, and I essentially demonstrated how each of these 4 flavors can contribute to the success of your design. So when you approach a design problem or when you want to analyze a specific design, it's not just one parameter that you want to focus on. There are about at least 4 parameters that you'd like to focus on and study the effects of to see their individual and simultaneous effects on the on the performance of the product. Here I walked through a simple static structural analysis. I threw this into a vibration environment. I threw this into a thermal environment to figure out the final shape of the component in case it's hot. And finally, I looked at what kind of force the customer needs to apply in order to assemble this component together. Now, what tools did we leverage today? We've leveraged just one tool, which is SolidWorks Simulation, that has each of these flavors distributed in 3 levels. There's a standard, professional, premium level. Now, the standard gives you all the static and durability testing. The professional gives you optimization and thermal and frequency analyses. And finally, the premium analysis is where you get into the nonlinear and vibration aspect of the analysis tool. Now, just to sum things up, like I said, we went over the four flavors of simulation. I attempted to demonstrate the benefit of CAD integrated analysis, where you can make quick design changes and figure out the effect of those design changes, and how you can streamline your design simulation workflow in order to accelerate product development. Thanks a lot for listening, guys.